Alright, so in our last video we went through the energy equation and a couple different forms of it, and now we're going to apply that to an actual question here. So imagine now we have some hydroelectric dam, and it's going to be taking water that's going through a turbine. It's going to have a generator attached to it, and it's going to be providing some power. So we have some reservoir up here that has enough water to supply the power, and we have some big hill here, some dam, and then of course it's going to drop off here, and then we're going to have the outlet somewhere down here. So we have two different levels of water, high and low, and the water is going to be allowed to be forced through some pipe here, and it's going to be connected to some turbine, and then it's going to have some outlet down below. So here's my turbine. Alright, and of course the turbine is going to be connected to some sort of generator here. And we're told that the efficiency of the turbine generator system is only 80%, which makes sense. It's not 100% efficient, so it's going to be equal to 0.8. Okay. Now we're also told that as the water is coming through here, it has a volume flow rate, so that's going to be our volume flow rate of 100 cubic meters per second. So that's the flow rate that's entering as it's before it goes through the turbine. Now these are pipes that are connected here, and of course pipes aren't perfect, so they have some friction in it, and it results in a head loss of 35 meters. So this is all information we're given in the question here. Now imagine the distance between here and here is going to be 120 meters. So that's the elevation difference, the distance, so the elevation is equal to 120 meters. So in a Bernoulli equation we always choose points 1 and point 2, and so we can choose point 1 here, and we can set one of them equal to 0 for the elevation, and of course the other one's going to be equal to 120 meters. So we'll just set here that h1 is equal to 120 meters, and that h2 then would be set to 0. So we have 0 down here and 120 meters up there. Okay, we've got the total head loss and the efficiency, and it asks us now to estimate what the electric power output would be. So the question for this is, we want to know here, what is the power output of the system? Okay, and so we're given now the volume flow rate. Let's calculate what the mass flow rate is. So the mass flow rate we derived in the previous video is just simply density multiplied by the volume flow rate. Now we have to know what the density of water is, and of course I think most of you know that it's just simply equal to 1,000 kilograms per cubic meter. Okay, and that's because we're dealing with water here. Alright, so we just have here 1,000 kilograms per cubic meter times the volume flow rate, which we were given, so multiplied by 100 cubic meters per second. Notice the cubic meters units cancel out, so the mass flow rate becomes 100,000 kilograms per second here, or just simply 10 to the 5 kilograms per second. Alright, so that is our mass flow rate. Now let's look at what's going on here. Some of the other terms that we have to consider have pressure in it, have the elevation, and have the velocity. So we've looked at the elevation here. Let's look at the pressure. Well, both of them are open to atmosphere, aren't they? There's no vacuum, they're not under pressure. So they're both equal, they're both under atmospheric pressure. So that means the pressure at point 1 and the pressure at point 2 are equal to atmospheric pressure, therefore they're equal to each other. Now the other thing that we have to look at is that when you have a large body of water, such as in a dam or a river or something like that, so this is a large body of water, and the same would be true at the outlet here. We have a large body. The velocity is not going to change the volume of the water at all. So the velocity of this water going down and the velocity of this water going up are negligible compared to the size of the actual body of water itself. So the water levels do not significantly change. So water levels, they're approximately constant. So if that's the case, and you do make always certain assumptions, so this is the one assumption you will make for large bodies of water. We're going to say that the velocity at point 1 is approximately equal to 0, which is approximately also equal to the velocity at point 2, because the water levels really aren't significantly changing. Alright, now we haven't been given the kinetic energy correction factor alpha, so we're going to assume that it is equal to 1 here. Now, we've got everything. We've got our H1, our H2, we have our P1 and P2 that they're equal to each other, and we have our velocities are also equal to each other. So now we're going to move on to actually solving this question. So I'm just going to get a new screen here. Alright. So let's write out our energy equation here. That's the first thing we got to do. So we have P1 divided by rho g plus the correction factor, kinetic energy correction factor, alpha 1, V1 squared divided by 2g plus H1 plus the head of the pump, if we have one or not, the useful head of the pump, is equal to P2 divided by rho g plus alpha 2 V2 squared divided by 2g plus H2, the second elevation, plus the head of the turbine, the extracted head of the turbine, plus the head loss. And that extracted head of the turbine is what actually comes out of the turbine. So now let's look term by term and see what we've got here and see what actually maybe we don't even include. So if P1 is equal to P2, so we can make that P1 was equal to P2, if we brought this term over to the other side, we're going to see that they're going to subtract off each other and go to 0. So these two terms, they go to 0 when they subtract off. And that's just simply because we have the P1 over rho g minus, we bring it over to the other side, over rho g, and these p's are the same, so that just simply equals to 0. So those aren't included. Now, we also noted that the velocities are equal to 0 as well, since the water level really isn't changing. So these two terms actually go to 0 too, and you'll find this is common in many questions where you apply the energy equation. Alright, now we set H2 equal to 0, and then H1 was our 120 meters. That was the elevation at the start of where the water was. Now, we rarely have a pump and a turbine in a question. In this question we have the turbine, which is going to be used to generate electricity. We don't have a pump, so this term doesn't even exist here. So all we've got left now, let's just write this out here. We've got the elevation, 120 meters, is equal to the head of the turbine, the extracted head of the turbine, plus the head loss. And we were actually told what the head loss was, and that was 35 meters. So plus 35 meters. Alright, so therefore, that's our therefore sign, the head of the turbine, we'll just bring that 35 over to the other side, and that's just equal to 85 meters. Alright, so we really reduced this equation quite quickly and just have one term left. Now, from our previous video, we saw that the head of the turbine, and this is where we are going to be using this eta, this efficiency that we were given of 80%, is equal to the power of the turbine, so that's W dot, the work per time, and that is divided by the efficiency times the mass flow rate times g, and that's why we needed to calculate this mass flow rate. And that's also equal to the extracted power of the turbine divided by m dot g, the mass flow rate times gravity. And again, we already just calculated that's equal to 85 meters. So we can rearrange here and solve for the extracted power of the turbine. So let's just do that here. The extracted power of the turbine is equal to 85 meters times, now our mass flow rate previously we calculated was 100,000 kilograms per second. So kilograms per second. And then of course G is just simply 9.81 meters per second squared. Alright, and when you multiply all that out, you're going to get 83,385,000. And our units are kilograms meters squared divided by seconds cubed. And that is actually a joule per second or a watt. And that's what it should be because we're working in units of power. So we can just say that this is 83,400, we'll just round here, kilowatts. Okay, we just rounded that number. All right, so that is the extracted energy of the power of the turbine. Now the last step is to apply the efficiency. Apply this eta here to find out what the actual power generated is from the turbine. All right, so the power of the turbine delivered is just simply equal to the efficiency times the power of the turbine extracted. So that's just going to be equal to 0.8 because we were told it was 80% times 83,400 kilowatts, which is just simply equal to 66,700 kilowatts. And there you have it. That's how you can solve a question that involves the energy equation where the Bernoulli equation won't be able to be applied due to power being delivered to or taken from the system and different head losses as a result of friction. All right, thank you very much.